So buffers are important. It's great to have my important statements emphasized up there. We've been rehearsing at home now. OK, so let's do a sample buffer problem. All right, suppose we have an acid, 0.1 moles of an acid, and 0.5 moles of its conjugate base added in the form of a salt. And so they're put into water and diluted to 1 liter. And you're given information about the Ka of the acid, 1.77 times 10 to the minus 4. And you're asked to calculate the pH. So what do you do? All right, first, it's always good to write the equation that you're talking about. And so you have acid and water forming hydronium ions and the conjugate base. So here, the acid is giving up a proton to the water, forming H3O plus and its conjugate base. Now we want to think about what happens at equilibrium. So we know how many moles we have, and we know what the total volume is. And in this table, we should be using molarity, but the math here is pretty easy because we have 1 mole in 1 liter, or 1, and 0.5 moles in 1 liter, or 0.5 for molarity. And now at equilibrium, what's going to happen? Well, when this equilibrates, some of this will go away, and more of these are going to be formed. So we have minus x over here, plus x, and plus x over there. And when we add it all together, we get 1 minus x, plus x, and 0.5 plus x. So the important thing to remember is in buffering problems, you have the acid and the conjugate. So we're used to seeing these tables where we only have something over here, and it's all 0 on the other side. But in a buffering problem, you have things on both sides from the very beginning. And that's a really important point. And that alone, if you can remember that, will get you a long way through this unit. So you remember that in a buffer, you've got to have both an acid and its conjugate base, or a base and its conjugate acid. So here we're talking about an acid and water. It's an acidic buffer. And so we can use our Ka value. We want to know what the concentrations are at equilibrium to calculate our pH. So we can use our Ka, and we can set it up. So we have on the top products over reactants. And we're not including water in this because it's dilute in solution, and so it's not changing very much. And now we can plug in our values. So we have 0.5 plus x, x over 1 minus x. All right, now this is just written again from the last slide. We can try an approximation, which is that x is small compared to 1 molar or 0.5 molar. And so we can get rid of the plus x and the minus x down here and just have the one x term, which makes it simpler to solve, but we'll have to go back and check that approximation in a few minutes. So making that approximation, we can calculate x as 3.54 times 10 to the minus 4 molar. And now we need to check that assumption. Well, you can probably guess it's going to be OK, because something times 10 to the minus 4 compared to 0.5 and 1, that's probably going to be OK that it's small. But our assumption here is that it needs to be less than 5%. And here it's 0.1%. So you could just take this value of x, divide it by the smaller of the two, 0.5, times 100, and calculate the percent ionization. And if it's less than 5%, you're OK. If it's more, you need to use the quadratic equation to solve the problem. So x here is our concentration of hydronium ion, which is great, because then we can easily calculate the pH. So pH, again, is minus log of the hydronium ion concentration. And so the pH here is 3.45. And again, significant figures. We'll be talking about this as we go through. The volume had it was 1.0 liters. And so we're going to have 2 significant figures after the decimal point, because the volume was limiting in significant figures.